welcome. Okay, so I know because I got messages about it. You've seen potentially that I posted an assignment because it took me forever to get through 1.3. So it wasn't a long weekend, but oh yeah, they can be tricky. What you can do if you're struggling with a question, then probably the easiest thing to do is if you text me a picture of your work, right? Or you can send it in an email, but it gets a little kind of tedious that way. So if you just want to text me a picture of the work and just that you've done, and just kind of say, I don't know what to do here. Can you give me a hint, or can you help me out, right? Depending on the question. And then I'll try to point you in the right direction. So what was I saying? Oh yeah, it wasn't really a long weekend, but it took me so long to get through 1.3 because I felt like we should be talking about everything that the textbook talks about. But I'm quickly realizing that we can't do that. So I had to really buckle down and just try to summarize the remaining sections. So I'm reworking everything. And so now I want to go through 1.5 today. And then if you have a read through 1.6 and 1.7, I'm hoping we'll have time to get into 1.6 today, but maybe not. So if you have a chance to read or maybe reread 1.6 and 1.7 for next day, because then I'll be able to do a kind of a quicker summary. And then I want to do 1.8 mostly in R for our lab on Friday. So I've decided to kick it old school. This is an old school kind of course. It's all theory and not too much applied. And so what I've done is I've picked questions out of the textbook. Remember that I posted chapter 1 of the textbook here. So once we get into chapter 2, chapter 3, I don't think I'm allowed to post those chapters, but what I can do and what I will do is I'll take little screenshots of the questions that I want and just I'll do it on my iPad, but so you'll have the questions, right? It might be useful to get an ebook, right? Some version of the textbook, but we'll be in chapter 1 for the remainder of this week and into next week. So it's all in there. So at the end of each section, starting with 1.2, there are exercises. So these are the ones that I'm referring to. So if I want you to do 1.2.1, that's from section 1.2, and it's question number 1. And so this first one, I think I wanted you to do because it's a cute one, just so we can get into the groove of things. Now I hope I picked that one. Pretty sure. Yeah, 1.2.1. So then for each section, right, from 1.2 or 1.3, there are a set number of questions. I do like to pick questions that have the answers in the back. So if you don't have a copy of the textbook, then I'll make those solutions available. They're just the single solutions, right? They're not going to help you a lot, but I find that it really does help me confirm what I've done, right? If I have some sort of solution that I can check against. So it's not the fully worked out solution, of course, it's just the final answer. But at least if you have a final answer to work towards, then that it makes it a lot, not easier, but a lot more structured. So that's what I like to do. And then I included a bonus that doesn't have a solution in the back that you can work through, right? So these can be tricky. So like I said, if you're having trouble with a problem, then just text me a picture of your work, the question that you're working on, and then I can have a look. Okay. So what I want you to do is just do your work on paper like this. That's probably the easiest thing. because if you're trying to type it up, unless you are very good at LaTeX, it's going to take you forever. So don't do that. Just write it out. If you have a tablet, great. Ultimately, I want you to save it as a single PDF. Okay, so you could write it on paper, and then to scan it, you can download a scanner app. Most phones have scanners built in. I find I'm on an iPhone, and I find that it's not, I find that my iPhone, it has a scanner built into Notes, but I didn't like that scanner. So I put some suggestions on there. I really like Scannable, or Cam Scanner is really popular. So there are lots of different scanner apps. And what I did was, when I first wanted to scan stuff with my phone, I just downloaded a bunch of free apps and I just tried them. How do I save it? How do I, send it to myself? That kind of thing. Yeah, so I do have a suggestion. It was a direct message, but I don't suggest typing it unless you really like typing it. But it's gonna be really slow. It's really hard to type it out. So you're welcome to, but yikes. Yeah. For me, it's a no. I'd rather just write it out by hand. And so I'm not expecting you to type it out at all. So then once you're finished, then you're going to upload that PDF, however you acquired it. And if you're not sure how to do that, then you can get in touch with me and I can show you around, but it's not that hard. And so here, let's see, when is this due? It's due next Tuesday. Okay, so assignment 1, which is on sections 1.2 and 1.3. Assignment number 1, sections 1.2 and 1.3 is due Tuesday. I think it's Tuesday, yep, October 12th. Basically at midnight, 11:59. That's when most, or pretty much all of my due dates are at midnight. Okay? So if you are dealing with time zones, maybe keep track of that. Okay. But obviously, if you're dealing with time zones, then you know what you're doing. Okay, so notice that we finished section 1.3 last day, and then now I'm starting 1.5. So the reason for that is because I've decided that conditional probability, you have seen it in Stat 230, so it's not going to be that new to you. So instead of kind of reviewing it now, I'm going to postpone it until it comes up again with conditional distributions. Okay, so note we will postpone. So we're not going to skip it. We're just going to postpone covering section 1.4. Until we introduce conditional distributions, which we don't know what they are yet, probably. But that's okay. Conditional distributions for random variables. They're coming. But first we need to talk about random variables, right? And so section 1.5 is on random variables. And there are two types of random variables that we can talk about. We can talk about discrete random variables, or we can talk about continuous random variables. And so 1.5 just kind of introduces some ideas. And the example that we're going to use is a discrete random variable. And then in 1.6 and 1.7, then we talk about the specifics of discrete random variables and continuous random variables. So today we're just going to introduce the idea of random variable. So 1.5, and I guess, yeah, I don't have any review. Can't remember for the life of me what we ended on last day. So I guess we'll leave it at that. Nice to start fresh though. So 1.5 is on random variables. And random variables are going to be a big player in this entire course. What we're going to do is we're going to talk about distributions of random variables, probabilities associated with random variables, different types of random variables. And so everything is just kind of centered around random variables. Okay. So in this course, we will primarily be interested in random variables, just kind of in general. We will primarily be interested in random variables. Okay. So a random variable, it takes some input value. So it is going to be kind of like a function. So it assigns exactly one value to each outcome. Okay. And so a random variable which we're going to abbreviate as RV. Sometimes I'll use a lowercase RV or capital RV. I think this capital RV is so funny because then it makes me think of a recreational vehicle, right? A camper. So I prefer to use this one most of the time just because I think it's funnier. But I mean, either way works. Random variable. So a random variable, capital X, and typically we use capital letters for random variables, and typically they are from the kind of the last part of the alphabet. Okay, so here, RVs are usually denoted by capital letters from the end of the alphabet. That's just a side note, okay? So X, Y, Z, we don't typically need more than, 3 or whatever random variables, but our most common one is X, of course. Okay. And so a random variable X assigns and maybe I'll put this kind of just in brackets here. Right around it. I got a direct message about all the different distributions and why/how did anyone feel the need to come up with them? And we will talk about some different distributions, but first we have to talk about random variables, of course. And then those random variables will follow a Poisson or an exponential distribution or a normal distribution, for example, right? And so then we'll get into the nitty gritty. So if you're here for the why of everything, this course is for you, because as you've seen in the textbook, They love telling you exactly why everything is the way that it is, right? So we'll get there. But first, random variables in general. Okay, so a random variable X assigns exactly one value and I just realized I forgot to move my mic up closer, but I'm not sure it matters. Seems to catch my voice anyways. But I like to be proper. Exactly one value, capital X of lowercase c, to each outcome c, which is a lowercase c, just like here, okay, in the sample space which we denote by C. Okay. So as a quick kind of example, X of H, we can assign it 0, or X of T, we can assign it 1. Okay, so it just assigns a numerical value to each outcome, right? H and T, it's implied that I'm flipping a coin and the outcome is either heads or tails, right? But now I'm recording them as 0, 1. You've probably seen dummy variables like this before, but at its root, you're talking about a random variable. We just never call it a random variable, usually in other courses, but now we do. Okay, so I want you to recall that the fancy set B is the set of events in the sample space. So if you have a sample space, that's just the list of outcomes, right? And then B is the set of all the possible subsets, right? And so B can be quite large. Of course, doesn't matter. So B is the set of events in the sample space. Okay. I'm really pleased with how this fancy B turned out. I'm going to try to replicate that again. It'll never happen. It'll never look as fancy as that. That's okay. So what we can do is we can use these and we can combine them to define the probability function. So the probability function, which assigns a number between 0 and 1, which assigns a number between 0 and 1. Oops. I was going to write out the words, but 0 and 1 to each event, which we'll just denote by normal C. It's a capital C. It's hard to tell, but the context will kind of lead you in the right direction because it's a subset of, here, I'm going to try to do pretty fancy still. Not as good, but pretty fancy. So it's an event, just a plain old C in the set of all the possible events, right, which are all the possible subsets of the sample space. So the probability function, remember, probabilities have to be between 0 and 1. We know that from a long time ago, right? And we looked at proofs around that. Okay, but so the probability function can be used to assign a probability to any set of numbers, which we'll denote by a capital D, to any set of numbers D. So what we're going to write is we're going to have P and then a subscript capital X. Now, we don't need that subscript capital X because we are only talking about one random variable X, but pretty soon we're going to be talking about multiple random variables, X, Y, Z, for example, right? So then we would need to denote it. So here, this is just denoting that this is the probability for this random variable X, okay? Of the set of numbers D, okay, is the same as the probability that X is in the set D, right, which is the probability that the set C, so of outcome C, such that X of C is in the set D. Oops. Make that just a plain D, curly brackets, square brackets. Okay, so these are all equivalent notations. Okay, I prefer this one, of course, but sometimes we'll have to use kind of some set notation here, remembering that C is an outcome, and the random variable assigned to the outcome C has to be in the set of D, which is the probability of any set of numbers. Okay. So this is kind of the most confusing part. Used to specify that the random variable is X. And maybe I'll write it just as that the RV is X. Okay, so you can, when you're reading these, you can ignore those little subscripts X's until you have multiple different variables, right? X, Y, Z. Then you'll need to keep track of which one's which. Okay. Okay. So what we're going to introduce first is called the probability mass function. You've seen a probability mass function before in Stat 230, but we probably called it a probability distribution. It's tricky because I didn't teach you Stat 230, so I'm not 100% sure on what was covered and what wasn't. But typically we talk about probability distributions, and so those are going to be called probability mass functions now. So the probability mass function is going to be shorthanded to PMF. Now, just as a heads up, there are going to be a lot of acronyms here. And so PMF is specific to a discrete random variable. We're going to solidify that later. So I'm not going to say that here, but just as a heads up, okay? And so there's the PMF, and then we're going to talk about the CDF, which is the cumulative distribution function. And then we're going to talk about the PDF, which is the probability distribution function, I think, or the probability density function maybe. And that's for continuous random variables. So we're not going to talk about that until 1.7. So we're going to introduce these concepts, but we've seen them all before. We just haven't assigned these fancy terms to them. Okay, so the probability mass function gives the probability of each possible outcome of each possible value, I should say, value the random variable can take on. This applies to discrete variables. Okay. So the probability mass function, just as a side note, you likely, I don't want to put anyone on the spot, but you likely remember probability distributions. Probability distributions from Stat 230, right? Where you had some outcome, maybe it was 1, 2, or 3, something like that. And the probability of X, usually we would denote it like that, is maybe 0.4, 0.1, and 0.5, right? You've probably seen something like that before, right? Where the outcome 1 has a probability of 0.4, the outcome 2 has a probability of 0.1, and the outcome 3 has a probability of 0.5. We say that this is a valid probability distribution because all the probabilities are between 0 and 1, and they add to 1. Okay. We know this is a valid probability distribution because, well, I'm going to leave out the part where the outcomes are disjoint. That is understood, or maybe why not? Because 1, the outcomes are disjoint, but that's kind of understood, right? You don't want to have any overlap, or you can't have any overlap in your outcomes. 2, each probability is between 0 and 1. Each P of A is between 0 and 1. And maybe I should use the same notation. Each P of X is between 0 and 1. And the total probability is 1. Right? So you probably remember that from Stat 230 or whatever other stats course you may have taken. Okay. So now we're going to make the same connection to the probability mass function, right? And because the probability mass function is kind of a little bit fancier, although it's the same thing as a probability distribution, but we have all this notation that we need to deal with. And so to be acceptable, as a PMF, a function must satisfy, and these are going to be the same rules as we just talked about, right? And so must satisfy first that the probability on the random variable X of the outcome X has to be between 0 and 1. And that's since P subscript X of X, notice that this is a capital X and this is a lowercase x. It's not life or death if we keep those, separate for right now. We could even drop this subscript X. So then it's just P of X. Is a probability. Is the probability that X equals X, which is a probability. Right? Probabilities, just as a rule, a general rule, have to be between 0 and 1, which we've established. The second part is that, and this is just a fancy summation, so the sum over all the x's in the set D. Now the set D was what? The set D, the probability function, skipping to the end of the comma, can be used to assign a probability to any set of numbers D. So remember, D is any number that could go into the probability function, okay? So then the sum of X over that are all in D, the sum of the probabilities here has to be 1. And I'll clarify where D, and I guess maybe this is should be a fancy D, where D is the set of allowable values of X. Okay. This condition is also called the normalization. Okay, and so I probably won't call it that, but it's good to keep an eye out, right? If you're reading the textbook and you see normalization, then now it should probably kind of trigger something. Whereas if you're converting to a Z-score, that's called standardization, right? So a little bit different, but I know I kind of went immediately to the Z-score, but that's not, it's normalization, not standardization. So this condition, just trying to keep it on the same page here, is known as normalization. Sort of. The only connection to the normal distribution that I can think of, not really, because all distributions have a sum of 1, right? Or a total area under the curve of 1. But yeah, so I can't think of any reason why we would use normalization, which is so similar in name to the normal distribution. But no, I can't think of a reason. But good call. Okay. So let's see here. I want to do an example. It's going to be a pretty basic example just to develop the ideas of all these different things. So the PMF, the CDF, and just what are they, right? Because then we're going to really rely on that later on. As an example, consider a simple random variable. A simple as in easy. It's not like a special term. A simple or easy random variable, or easy, simple, let's call it this instead, so there's no confusion. A simple example of a random variable. What if I flip 3 coins, or potentially the same coin 3 times over? It doesn't matter. Oh, you know what? Instead of sending direct messages to me, because these are really good questions, would you mind sending it to everyone instead? Just that last part, because does it mean every variable has equal chance of selection? Not necessarily. It just means that the sum of the probabilities has to be 1, is really all it says. Nice, thank you. Because I think everyone can benefit from reading these. Okay. I'll have to look it up. Get carried away. You just want to chat with me, not everyone else. That's fine. But they're good questions, so you should be proud of them. All right. Oh yeah, so a simple example, let's say we flip a coin 3 times and we count how many heads we have. Alternatively, of course, we could count the number of tails, but they're the same, right? So, so if we flip a coin, flip it, so I am going to copy what I have because now I'm realizing how silly it is, but flip 3 coins, or 1 coin 3 times. We're going to assume that they're the same, and count the number of heads. And count the number of heads. How many possible outcomes are there? That's a good place to start, right? And so for the multiplication rule, I like to just do little slots. So in this case, oops. In this case, there are coin 1, or flip 1, 2, and 3, let's say. There are 2 times 2 times 2, which is 8 possible outcomes in the sample space, or 8 outcomes in the sample space. I always find that that's a good place to start. If I can figure out how many possible outcomes I have, then it's always easier for me to figure out what those outcomes are, right? Especially if I want to draw them out or write them out. So what we can do here is you can try listing all the 8 possible outcomes. And so I'm going to start with head, 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 tail. There's no particular order here. It's just the set of these combinations. Head, tail, head, head, tail, tail. Usually you'll want to have some sort of method to your madness when you're listing these, right? So start with the heads, 2 heads, and then move to head, tail, and then move to tail, tail, head, so forth. Tail, head, tail, head, tail, 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 head, and tail, tail, tail. There are situations where we can't list all the possible outcomes, but it certainly helps if we can see them all now that we're starting. I'm just going to count to make sure that I got all 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, good. So these are all the possible outcomes if I flip a coin 3 times. Okay. we're going to assume that the coins are fair. So I'll say that if the coin is fair, the probability of each outcome is going to be 1 in 8. The probability of each outcome is 1/8, which is 0.125, right? That's assuming that it's fair, which we do. So now, right, what we were interested in was count the number of heads. So X, our random variable, is going to be the number of heads, right? That could change depending on the question, right? And so X is just going to be whatever we were interested in. So if we let X be the number of heads, in each outcome, then we can say something kind of lofty like the probability of X, where it's the set of 1 head, is the same as the probability that the set where C, such that X of C is contained in the set of all the possible outcomes with just 1 head. So that's going to be head, tail, 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 head, tail, head, tail, tail. Those are all the possible outcomes where you only have 1 head, right? And so this is the shorthand that we're going to use, right? The probability of 1 is typically just how we write it, P of 1, right? That's extreme shorthand of this. But technically what we're saying is, well, if C is the outcome where X of C is in somewhere in one of these 3 out of the 8, right? That's technically what we're saying when we say P of 1. Okay. So we can visualize this, right? We can take each of our 8 possible outcomes and we can put them into categories. Because I'm flipping the coin 3 times, I know that I could have 0 heads, I could have 1 head, 2 head, or 3 heads. There's no more and no less, no fewer heads that are possible. So to visualize this, we can organize the outcomes. So what I have is X equal to some lowercase x. Well, it could be 0, it could be 1, it could be 2, or it could be 3. I'm going to bump this up 1 line here because I can. So now if I go through all my outcomes and I classify them as either having 0, 1, 2, or 3 heads, then I can write them under the respective categories. So I can work my way through here and I can have this first one confusingly goes in the 3 category, right? Because it's got 3 heads. And I'm gonna just copy this down for now so I can see them so I don't have to scroll around so much. So here, if I take head, and you know what? I'll put them here so that they can just be in there. So now I can see them, right? So head, would go in the 3 category, right? The next one has 2 heads, so I would put head, head, tail in the 2 category. Head, tail, head still has 2 heads, and so head, tail, head goes in that category. Head, tail, tail only has 1 head, right? So head, tail, tail goes in the 1 category. Tail, head, head also has 2 heads. Tail, head, tail has 1 head. Tail, tail, head has 1 head, and tail, tail, tail is the only option where I have just only tails. Okay. So now, when I can see all the possible outcomes, right, then it's easy to see what the probabilities of each of these are, right? The probability that x equals x is going to be, well, 1 in 8 or 3 in 8. This should look like an 8. 3 in 8 or 1 in 8. Okay. We usually write this more elegantly using a piecewise defined function. So, or more elegantly, we write that P, and sorry, that should be a capital X, Px of x is equivalent to it's pretty well the same thing as an equal to. It just means that these 2 things are equivalent to each other. And so they mean the same thing. So it's equivalent to the probability that x equals x, which is either 1.25, or sorry, 0.125, 0.375, 0.375, 0.125, or potentially 0, right? If it's anything else. So that's if x equals 0, if x equals 1, if x equals 2, if x equals 3, and 0 otherwise. And show that as a piecewise function. Okay. That's the same information that we just developed in the table, but it's a little bit cleaner, it's a little bit nicer looking, and this is the notation that we'll be using. But notice that it is the same as what we're kind of used to seeing. Okay. So if we want to, we can plot these if we want to. They're going to be kind of boring, right? But what the plot would look like, we could plot this. So what would we have on the y-axis? We would have Px of x ranging between what values? Between 0 and 1 typically, but our maximum value on the y-axis is going to be 0.375. So what I'm going to do is I'm just going to cheat, and I'm only going to have kind of cutoff points here at 0.125, and then maybe here at 0.375. Only because they're the ones that I'm interested in. But of course, if we were actually going to draw a graph, we'd have better axes and that type of thing. So then if I think about, okay, my x being 0, 1, 2, or 3, then I'm going to put my 0 here because it's a category, 0, 1, 2, or 3. What I'm going to have is I'm going to have a bar for 0, which is the height of 0.125. A bar at x equals 1, which goes up to 0.375. Same thing for at x equals 2 and x equals 3, the bar goes to 0.125 again. And these are the values of x, right? Which are essentially, they're discrete, but when they're discrete, we can think of them sort of as categorical variables, sort of. Because we have categories, right? These discrete categories 0, 1, 2, 3. Okay. Sort of. Okay. So what we're going to find is that, okay, if we know the probabilities, so if we know these probability distributions or these probability mass functions, that's great. Then we can go ahead and use that. But what's going to happen a lot of the time is that we're not going to have the probability mass function, okay? But we will have access to the cumulative distribution function. So let's see here. As we will see, it is not always possible to define a PMF. Okay, or I guess I shouldn't put a period there, I'm not done. So it's useful to define a more generally applicable construct, which we call the CDF, the cumulative distribution function, which you have probably already seen, right? Especially for the normal distribution, if you think back to your Z table or even your T tables, right? Those are giving you the area under the curve up to a certain point. So that would be a cumulative distribution function. So usually that's what we end up talking about because we don't always have the probability mass function. So it is useful to define a more generally applicable, applicable construct the cumulative distribution function. Which we call the CDF. We've already seen, note, you've likely seen the cumulative distribution function for the random variable that we just introduced, and we're going to work through it. But another time that you've already seen a CDF is with the Z table, specifically the Z table, right? Kind of in a roundabout way, the T table as well, but it's not explicit. So note, you have already seen at least one CDF since the Z table is a list of it depends on the T table, but remember the T table, you have to find the degrees of freedom, and then it's got the areas under the curve up top or maybe down below, depending on which version of the table you used. But so the areas under the curve are not in the body of the table, they're there, but you'd have to do a little bit of work, right? In the body of the table, in the T table, are T values, right? And so then you have to kind of, so they are CDFs as well, but in kind of a weird way, because usually the T table will only give the area in the tail, not necessarily the area below that value. There are many different types of T tables, so I'm not sure which one you've used, but if it's the one I'm thinking of, it's there, but it's not explicit. So, but the Z table is explicit, right? If I give it a Z of, I don't know, negative 1.96, then I should get 0.025, right? That's the only one I can remember. And that means that the area up to and including negative 1.96 is 0.025 or 2.5%. Right? So those are CDFs. Okay, good. So what we're going to say is that we're going to use the notation of a capital F to denote a CDF. We will let capital F of X, so a random variable X, denote a CDF of the random variable X. Okay, just as notation. So then what we're going to say is that the Fx of X is equivalent to, now we can kind of read it as equals, but I mean, should be equivalent to the probability that X is less than or equal to X, right? The probability that X is less than or equal to X, which is really the area to the left of X equals X. The area under the curve to the left of X equal to X. Okay. Probabilities are still areas under the curve. That's not going to change. So in our case, we said that Fx of X, which is equivalent to, so just rewriting that out, X less than or equal to X, which in the previous case, right, you can have 0 heads, you could have 1 head, you could have 0 or 1, right? You could have 2 heads, you could have 0, 1, or 2. So notice how I'm just accumulating as I keep going, right? And so here, the probability is 0 if X is less than 0. So if you have less than 0 heads, the probability of that happening is 0, right? If X is down to 0, so including 0 now, but just up to 1, but not quite at 1, right? Because remember here, the probability of X equals 0, that's where we get this probability of 0.125. So everything between 0 and up to 1, but not quite including 1, is going to have a probability of 0.125. Oh yeah, I'll stay here just a little bit longer just to show you where the next few numbers are. So then if I go between 0 and 2, think there's an error in my notes now that I think about it. Let me just grab my calculator because I'm not adding. Why was I not adding? 0.125 plus 0.375. That would be the cumulative distribution up to and including 1, right? So that's 0.5. And then I add 0.375, which would put me at 0.875 up to and including 2. And then up to and including 3, I reach 1, and then there's nothing after that. Okay, so I'm noticing okay, I'm on board with my notes. Just had to sell myself on them. Okay, so the cumulative distribution function between 0 and 1 is going to be the 0.125. I am going to put curly brackets here, but I just want to list all the outcomes so that my curly bracket looks nice, or tries to look nice at least. So then if x is between 1 and 2, and I'll kind of, I get up to 0.5. So this is where I'll show you what I have in my notes. So if x is between 1 and 2, what I reacted to was it should just be up to and including 2. But because the 0 to 1 is already taken care of, the 0.5 actually only applies between 1 and 2, right? So even though it does take into account the probability of being less than or including, or up to 2, sorry, it really only applies if it's between 1 and 2. Okay. So that's why. But that's why I had to convince myself. It took a little bit, but I got there. So then 0.875 is if x is between 2 and 3. So including 2, but not including 3. And then it's a 1 if x is greater than or equal to 3, right? Anything larger than 3, the probability is going to be 1. Or the probability of less than 3 heads, including 3 heads, is 1, right? If you toss a coin 3 times. So now I'm going to draw there my curly bracket. Okay. So what it looks like, right? So which would look like this. Now, if I quickly draw my y-axis, because that's the one I want to get right here, my CDF is going to go from 0 to 1, right? And so what I'm going to do is I'm going to have 0.2, 0.4, 0.6, 0.8. I need one more. 0.2, 0.4, 0.6, 0.8, 1.0. So then here on my x-axis is going to be my x. 0.0, I'm going to put it on the x-axis, of course. What I am going to do is I want to show values just a little bit past 0, to the left of 0. So because x can have less than 0, it can't really because the probability is 0, but maybe what I'll do is I'll draw this axis here. And the origin is, of course, going to be 0, 0. So now I'm going to have cutoff points here at 1, at 2, and at 3. I really overshot it, but that's okay. Maybe what I'll do is I'll do a partial erase here because I don't need all of that. Make room. Okay, so then the probability or the cumulative distribution function is going to look like this. It's going to be a stepwise function. So it's going to go here at 0 up until it reaches 0. Right? And then, so x less than 0, it's going to be 0, not including 0. Right? So here, I want to highlight that and maybe like this with an open circle. Okay? Because once I hit 0, right? 0 is an option. It's a possible outcome. It's a possible number of heads. So between 0 and 1, not including 1, I bump it up to 0.125. So maybe that's something here. And I'm going to show that it's open with an open dot, right? It's not including 1. Okay. So then 0.5 between 1 and 2. So let's do a closed dot here, including 1, but not including 2. Whoops, I took it too far. Okay. 0.875 between 2 and 3, 0.875, maybe here to 3. And anything greater than 3 is at 1. Okay, so it does keep going. But usually we don't need to show that, right? One thing that we're going to notice here is that we are dealing with a right continuous function, okay? Meaning that as we approach the point from the right, evaluating the function at x equals a gives us f of a. Right, and so, or the limit, I should say. Oh, no one likes limits, no one. But in this case, they're easy enough and they make sense, right? And so what we notice is that if I take the limit as x approaches 2 from the right, then the function at 2 is 0.875, right? Whereas if I take the limit as x approaches 2 from the left, right, then the limit is not the same as the function at 2, right? And so we say it's right continuous because it's continuous when I approach it from the right, but it's not left continuous because it's not continuous when I approach it from the left. So here, notice that the CDF, which we denote by fx of x, is not continuous because we've got this stepwise function, right? So we know it's not continuous. A continuous function we can draw with, I made it not a function by looping back on itself, but we can draw with just a continuous line here, right? Here I had to lift my pen, so I know it's not continuous. But it is right continuous. Or continuous from the right. I know Would a bar graph convey the same idea in terms of continuity? You could, but the bars, you want to show that it's taking into account the previous probabilities. So I wouldn't really use the bars. I think I prefer this because then I can see that there's actually a step. Whereas if I tilt these, right, if I kind of tilt them on the x-axis, then that would look like the probability mass function, but it doesn't highlight that everything between 0 and 1 has this probability. And then if I go to 1 and 2, so I have to think about it, but my gut says no. Okay. Oh yeah, so continuous from the right or right continuous, depending on where you took your Calc 1 course, right? If you took it with us at the college, we tend to use Stewart's calculus. And so I'll introduce that notation as well. But it's nice to see other notation just so we're not so scared of it, right? And so right continuous, that is the limit. Oh, I guess I should write it nicer. That didn't work. The limit as x goes down to x naught. So this is the notation that the textbook uses of fx of x is fx of x naught. Or if you prefer, usually we would have written the limit as x approaches a from the right. That's how I'm used to writing it. Of f of x is f of a. Right. Or maybe I should say, maybe I should talk about the same function. Capital F. Same idea though. And if you want to, you could even throw on these little subscripts, but you don't have to. Okay. Good. Oh, great. Let's clarify. So the limit, so when we say things are continuous from the right or right continuous, what we're saying is that here, if I'm coming in from the right, so I'm approaching this point here at x equals 1, for example, then in order to be continuous or right continuous, then the limit as I approach x equals 1 is going to be the same as the function at 1, right? And so here, I'll say notice again. I keep saying notice, but I'll do it in terms of notice at x equals 1, right? We can talk about the limit as x approaches 1 from the right. So I'm going to use that notation that I'm used to, and you're probably used to as well, maybe. Approaches 1 from the right of fx of x is going to be, so the limit of this function as x approaches 1 from the right is equal to the function at 1, which is what? 0.12 or 0.5. I see that you got it, but I may as well finish it. versus the limit as x approaches 1 from the left of this function does not equal, let's see here. It does equal the function at 0, right? So here it equals the function between 0 and 1, but not including 1. So now I'm approaching x equals 1 from the left, but it's not evaluated here at x equals 1. And so it's the same as the function evaluated at 0, which is not the function at 1. So therefore, not left continuous. Good. So instead of starting 1.6 today, I'll leave it there. And then if you have any questions, let me know. But otherwise, we'll do kind of a mashup of 1.6 and 1.7 next day. So if you have any questions, let me know. Otherwise, I'll see you then.